Hello and welcome to our presentation of the Home Energy Appliance Device, H.E.A.D. Our group consisted of 4 UC Berkeley IEOR students and 1 energy engineering student.
In North America, most homes are equipped with a multitude of appliances such as washer, dryer, microwaves, refrigerators, etc. that use electricity for their operation. For our product, we want to help households simulate their energy usage and determine if they could benefit from installing a demand response system for their home.
With 25 million households in 2009 and $40 billion spent on energy by these homes, controlling the energy usage efficiently is an important problem that can lead to big savings.
Energy providers like PG&E often ask their customers to reduce or even completely stop their energy usage during peak hours due to capacity constraints, which allows them to serve all their customers without building more infrastructure. This is where the demand response comes from. It is a response to energy usage that goes above the capacity of the energy provider.
We crafted a solution using discrete event simulation in SymPy Python.
Our product first gathers usage data to build a probability table for the appliances and their usage in a resident's home. Then we simulate for many days and determine, first, how much money could the resident save from modifying the time that they use their appliances. Second, whether or not they will save money from using the utility demand reductions.
So what you're looking at now is the diagram for a single simulation run. To start off each run, we create a home energy automation device, which in turn creates a series of objects. These objects then self-schedule and add usage events to the events list. In the beginning, the home energy automation device also creates a demand response event, which removes usage events at key times to simulate demand response.
Some of the key assumptions we make for our model include 1. A transient entity model, 2. Assuming a probability distribution for the time between starts of appliances and for the length of time the appliance is running, and 3. That any appliance which can respond to load shifting signals does so instantly and without user interaction.
And some questions our product aims to answer include 1. What is the amount of money we spend on energy? And 2. How much money does user save from demand response? And 3. Is a home energy automation system worth its cost?
We have the front-end UI for our product. As you can see, it allows our user to input the data that we require to construct our probability distributions for each appliance. We can select from refrigerators, air conditioners, heaters, washers, and more. Then the user selects a start and end time for their feasible region of usage. This means the earliest time that they would start using this appliance and the latest time that they would end using the appliance. Then they select the service time, which is how long the appliance will be running for, and the number of times that they would use this appliance in a day. We have an informational screen that summarizes this information. And once that's done, the user simply clicks Save Money Now, and the simulation run starts, and the Python will output many different informational graphs and numbers.
This is the graphical output of the H.E.A.D device. The graph on the top is a histogram of energy used by hour of the day. Events in red are those that have been rescheduled by demand response. The middle graph shows cumulative electricity expenditure. The bottom graph shows demand response savings over time. As you can see, some portions of the line are horizontal, indicating that demand response was not used on that day. Over on the right, you can see the number of events of each type followed by an events list.
In conclusion, we were able to successfully build a tool leveraging discrete event simulation that was able to provide residential customers with the demand response cost savings.
Future work could include, firstly, inputting a larger data set of residential customers to run our simulation to obtain more accurate, more realistic results.
Next, we were thinking about determining the optimal break-even point for a customer to purchase the H.E.A.D product.
And finally, we were thinking about expanding our simulation to include the cost-benefit analysis of purchasing alternative energy management tools, such as the Tesla battery, Nest thermostat, solar panels, smart thermostats, or many more. So thank you for watching our video. Again, this is our team. We can be reached at the below email addresses if you have any questions or wish to purchase our product or have any inquiries of any sort. We would like to thank you for your time, and go Bears!
Go Bears!